We went through solving multi-step equations with multiple variables yesterday. We talked about a good majority of those. Go to this page. Anyone else need that copy of those notes? Okay, so yesterday we were solving and we got specific solutions. Today we're going to talk about special case solutions. So you won't really know it's a special case until you start to solve it. So we're going to solve these two and see what happens. Alright, so number one, what's our first step? Distribute. We have 5x plus 5 equals 15x minus 12 minus 10x. What's our next step? Combine like terms, but just on one side, so the 15x and the negative 10x. Okay. Before we continue, I want you to look at this. Tell me what you notice about these two sides. Say that again. Anything that you see.
There are two 5x's.
Okay, so they both have a 5x. Anything else?
Do all numbers are positive? Okay.
Except for the 12.
Yeah.
4. Okay, so they both have 5x's. They have different numbers here. That'll be helpful later when we're looking back at what type of case this is. Okay, so let's pick something we want to move. What do we want to move?
Plus 5.
So if we're getting rid of the 5, we would subtract it to the other side. Remember, we could do these simultaneously, so if we're moving the constants to the right, we can move the variable terms to the left. But what happens when we move the variable terms? They cancel. They cancel out. There's going to be nothing left. So we would just put 0 equals negative 17. This is how you know you have a special case, because your variables have canceled and you get something that looks like this. Now, does 0 equal negative 17? Is that a true statement? No. So because that's not a true statement, this is no solution. So anytime your variables cancel and you're left with two numbers that don't equal each other, is no solution. Now, you could get your variables to cancel by accident. Be careful. But if they actually cancel and you're left with two different numbers, this will be no solution. If when you start solving, you see something like this where they have the same coefficient but two different constants, that's also going to tell you this is going to be no solution. So if you see that and remember that from this stage, you don't have to keep solving. You can say at this step, it would be no solution. But if you don't remember that and solve it all the way, that's also fine. So I think this is blanked out on yours, but I'm just going to move this down. You can write this if you want. So when we solve equations and we get a number, we can put that back in and see does it work. For no solution, whatever number you choose, none of them will ever work. So I can put in 1, I can put in 10, negative a million, 100, put in decimals, none of those would ever work. So you would get no solution. Okay. Questions on how no solution works? Let's try this next one. Now this one, because of the name, you'll already kind of guess what type of solution this will be, but we'll still solve it anyway. So just like number 1, distribute. 6b minus 3 minus 7 equals 6b minus 10. Combine your left terms. What do you notice about this line? The 6b's are the same. And the 10s are also the same. So really, these are identical on both sides. So that's going to help us figure out that this is this special case. Your calculator number is the same. Right, so then what do we want to move first? The 6b. So if we're subtracting 6b both sides, whether you did that from right or left, then we also have to get rid of the 10s by adding. What happens when we do all of that?
0 equals 10.
Everything becomes 0.
But you, oh.
So then this is your other special case where your variables cancel, but you end up with a true statement, 0 equals 0. That would be infinitely many solutions, or IMS. That means an opposite of no solution. That every single number in the world that you know, you could put in and it would always work. 1, 10, 20, 50, 100, a million. Keep going. And all the negatives and all the decimals and all the fractions, all of them. They would all work. Right? Just like with no solution. If you see that this has the same coefficient and the same constant, that's going to tell you that's infinitely many. So if you see that, you could stop there, say this is infinitely many, or if you want to keep solving, you could do that as well. So far, do you have questions on how no solution or infinitely many solutions work? I'm going to have you try 2 of these, and then you'll have 2 to go back to later. Let's do 3 and 4. I'll give you some time to work through those. While you're working through those, I'm going to give you a sheet of paper. It's going to talk about the different types of solutions and how you can know which type is which, but also what it looks like on Desmos. And I'm going to have you add something in here in a bit. So work through that, work together. Okay, you can do that one. Huh? You can do that one. If you need your paper, you can bring that up. And then when you're ready, you can use your paper to switch the board. Oh. The type of solution, yeah. We agree or disagree? Let's see some nods, there's some thumbs up. We should agree this was infinitely many solutions. Everything should have canceled. We get the same thing on both sides. All of those things, infinitely many solution. Anyone want to do number 4? Go for it. Now, with number 4, you had some choices. You could have combined like terms and then started moving things. You could have moved things and then combined like terms. That part didn't really matter order-wise, as long as eventually you did them all. But if you combine your like terms first, you would have saw that on both sides you have the same coefficient at 2/5, but different constants. So at that point you could have said this is going to be no solution. But if you kept going, added 7 or subtracted 3, and then got rid of the 2/5, you would have saw that that is no solution. Okay. Really quickly, look at that paper I just gave you. On one side, this side that says determining the type of solution. I don't have this up here. I just want you to fill out the top part really quickly. Look at the variable terms. For one solution, the variable terms are different. Or you can say the coefficients are different. For infinitely many solutions, the variable terms are the same. Both sides are identical. For no solution, variable terms are the same, but both sides aren't the same.
Wait, what was the first one? A variable terms
Are different.
not for no solution. For no solution.
For no solution, the variable terms are the same, but both sides are not equal. Okay. And then once you have those, so if you are solving different equations and you get to that step, those words will help you determine how many types of solutions, one, none, or infinitely many, how many solutions you have. And look on the back. So I'm just going to show this on decimals. Okay. So one type of solution will look like a line. So I'm just going to put in the solution from the back. 3x minus 5 equals 7x plus 3. It looks like a line. You get a solution. What we talked about the other day to check your work. That's one solution. Infinitely many will look like this. Actually, it won't look like anything, but I'll show you what happens. So when you put in the entire thing for infinitely many, nothing will look. So what you'll have to do is put this in separately, put one piece of it in, and then another piece of it in elsewhere. I'm going to delete part of it. And the computer is not so much. Alright, so I don't know if you saw what just happened. But they graphed on top of each other. So you can see the blue dots on top of the green line. So they overlap each other. So if you're checking yourself at Desmos, that's what's going to happen. The same thing is going to happen for no solution. If you put it in all together, nothing will appear. You won't see anything, but if you put them in separately, you'll see two separate lines. Later when we get into slope and things like that, this will make more sense, but these are going to be parallel lines, they never intersect. They go in the same direction, things like that. Right? So when checking your solution in Desmos, be on the lookout for those different things. If you put those in and they don't appear, you have to separate it and then see what you're looking for. Right? Go on to the next page in your notes. So these are more word problems, but more so with solving equations with variables on both sides. So we'll do, if we have time, all three, if not, as many as we can. Alright, so for number one, if we're finding the value of x so that the rectangles have the same area, we have to talk about how do we find the area of a rectangle. The other day we were talking about perimeter, where we add up all the sides. So how do we find the area of a rectangle?
Length times width.
Multiply the two sides, length times width. Now, in this case, they have the length and the width as variables or numbers. So really, we're just going to multiply this side by this side, and this side by this side. But if they have the same area, what does that tell us?
What do you mean?
Like, if I know the area is going to be the same, when I multiply these and when I multiply these, they're going to be the same. How could I write that as an equation? How could I say this is the same as this?
That equals
Close equals. 12x equals 16 times x minus 2. So without really saying much, it tells you to find the area, so you have to know how to find the area. And then because they are the same, you have to know to set them equal to each other. Then it becomes an equation, then we can solve.
So we have to figure out if it have the same area.
So that one more time.
So we have to figure out if it have the same area.
So they should have the same area once we solve it.
Oh.
Let's go ahead and distribute. What would be our next step?
Minus 12. No, minus 16.
So if you subtracted 12, you could do that. But then you'd have equals, 0 equals, everything over here, you would have to move the x term back. So you could do that, but you would just create an extra step. But to not create an extra step, we could just get rid of 16. And then solve from there. So the x equals 8. Now this is not the area. This is just this part. So to actually find the area, we have to multiply 8 and 12, or 6 and 16. What is that area?
Why did you do 8 minus 2?
This was x minus 2. We just
Oh.
figured out that x was 8.
Oh, yeah.
What is that area?
96.
96.
So you
Here we
just
don't
have to figure out what x was?
We had to figure out what x was in the area to make sure they were the same. So this one doesn't have units, so we don't have to put units for this one, but generally they would. Okay. Questions on that one? Okay. Let's read number 2. Chris has saved twice the number of quarters that Nora saved plus 6. The number of quarters Chris saved is also 5 times the difference of the number of quarters Nora saved and Kurt. Write and solve an equation to find the number of quarters they each saved. Alright, so let's find important information first.
Plus 6.
I'll put and 3. Is that all this right?
And then the question.
I'm also gonna highlight this part is also, because that tells us we're gonna set the two equal to each other. Alright. So because everything that Chris has saved is based on Nora's, we're gonna set a variable for Nora. And just call that N. Number of quarters Nora saved. And then twice the number of quarters Nora saved plus 6 would be what?
Wait, what?
Twice the number of quarters that Nora saved plus 6.
So the 2
And plus 6 is also, so that's going to be our equals, 5 times the difference of the number of quarters and 3. So now we have our equation, now we can solve. Looking at our coefficients, because these are different, what type of solution are we going to get? Or how many, I should say. 1, none, or infinitely many? 1. They're different. Right? So what do we want to move first? Or we would move this by doing what? Subtracting 5n to the other side. Because we moved all the variable terms to the left, let's move the constant to the right, subtract 6. And divide. So that the number of quarters Nora saved is 3. Our unit there would be quarters. But the question asks us to find how much they each save. So because these sides are equal to each other, you can put 3 into this side, or you can put 3 into this side. So let's do this. These 4 tables, do this side, 2n plus 6, put 3 in. These 4 tables, 5 tables, put 5n minus 3, put 3 in. Figure out what you get.
Wait, what?
So you guys are doing 2n plus 6, we're putting 3 in. You guys are doing 5n minus 3, but putting 3 in. You should get the same thing.
So we do 2 times 3 plus 6. That's 12.
Did we get 12 over here as well? Yes. So then we figured out that Chris would have saved 12 while Nora saved 3. This word problem is kind of made up because we wouldn't say all these words, twice the difference and all these things. We would just say however much he has. So more of your word problems are going to be like what we saw the other day than these, but it's possible that you may see these as well. Okay, questions on that one before we do this last one? I want you guys to try this last one. So read through it, find important information, set it up, solve it, and we'll come back and talk about it. got negative 45 equals x, or x equals negative 45, that was the correct answer. If you didn't, and at this step you multiplied by 1/3, fix that. So we can multiply by the reciprocal or divide by the fraction, but we can't mix those up. Do we have any questions on this problem?
So for this, we don't have to like check it on the calculator. We don't have to.
You can. So I checked it in Desmos. You had to zoom out, but it was negative 45. If you did check it in the calculator, you would have put negative 45 into all of the x's. In a moment, I'm going to let you put your calculators back. The same practice problems from multi-step and word problems are up here as well as a new one. Your number of solutions. So you can solve these, figure out which type or number of solutions. Make sure you're doing your delta math. You guys have 3 due tomorrow. So you can be working on that. You can put your calculators up.